recording. So this is the second lecture of the VLE, Vapor Liquid Equilibrium, and just want to quickly remind you about the updated schedule. So the first important thing is we are having the exam coming next Tuesday, still from 8:30 to 10:45, and the coverage will be from the excess property all the way up to the mixing the activity coefficient and the vapor liquid equilibrium. And then you can see that after the Thanksgiving holiday, we are going to cover the last part of the thermal, which is the reaction equilibrium. Last chapter we are going to cover. So that's all we are going to finish before celebrating this wonderful semester. Okay, any questions so far?
Nope.
No, good. So if we move on to have a quick review of the vapor liquid equilibrium we were talking about this Tuesday, I hope now you have this uh, general idea that we are going to have a mixture and multiple components, multiple phases, and depending on the pressure we are going to have, or uh, depending on the intermolecular interaction we are going to have out of the liquid phase, then from simple to the more general case, we are going to have the following equations, right? So this is the low pressure Raoult's rule. And then for the liquid phase, we are going to use the ideal solution assumption. And moving to the next step, we cannot assume the ideal solution for the liquid, then we need to look for the activity coefficient. Uh, then for the most general case, we have to treat both liquid and the vapor as the real and complicated phases, and we need to calculate the activity coefficient as well as the fugacity coefficient. We were also talking about last, no, this Tuesday, that for the 4 different types of calculations, VLE vapor liquid calculations. So if we know the temperature and the liquid composition, then we can easily calculate the total pressure and the vapor phase. Similarly, if we know the temperature and vapor, then we can figure out the liquid. If we know the pressure instead of temperature, then it's a little bit of extra work. We need to run the iteration, right? So recall that we need to, firstly, we need to figure out the temperature will be coming out of, no, the pressure, uh, no, yeah, it's the temperature. The temperature will be coming out of the minimal and the maximum region, assuming there's only a component 1 and component 2. So this is how we are going to start the initial gas. Then the other idea is that we need to, instead of looking at the saturation pressure from Antonio equation as their individual values, we need to look for their ratio, right? And then we will try to iterate to figure out the temperature. Once the temperature is known, then the remaining should be straightforward. So that is what we were talking about this Tuesday. Uh, and I added some slides based on the draft version I uploaded last night. So here I want to take a look at the phase diagram. As we were quite comfortable after those discussions, we know that in theory, if I know the species A and B, then of course I'm going to have all their pristine properties, right? So including the critical, including those omega value, including those ABC coefficients for the Antonio equation, so that we should be able to figure out P, T, X, and Y. So we are able to determine the exact composition of the system at any temperature and pressure. So this is indeed how we can construct the phase diagram. So here, if we take a look at the TXY diagram, so this is TXY, and in order to do that, we need to have a known pressure, and over here, try to recall the Gibbs phase rule. That is how we need to figure out how many independent parameters we are going to monitor. So now if you look at that the phase diagram Txy, number one is we need to figure out where would it be the vapor line, where would it be the liquid line. So that is to identify Tx and Ty, right? So I hope this is sort of straightforward. Increasing the temperature, of course, you are going to have the vapor phase. So the top region would be the vapor, the low temperature, the bottom region would be the liquid phase. And then, of course, if you are moving from the liquid, trying to receive the vapor, and we call this as the bubble line calculation or bubble pressure calculation. So here, if we are moving from the subcooled liquid, this is the pure liquid or mixture 1 and 2, then we keep increasing without changing the liquid composition. So we have this vertical line, and then at point B, we are going to receive the first bubble. So this is why we call this PB as the bubble pressure, right? And then the corresponding bubble phase, this is a B prime, then we should be able to read the in the vapor phase, what would be the ratio of Y1 over Y2, right? And then if we keep moving at this point C, we are going to have the last liquid drop, and moving all the way to high temperature, we are going to have the pure superheated vapor phase. So here it's we always have this 1 and 2 mixture, and it's just the ratio of each phase will be changing as you are moving along the temperature increase path. Okay, and the B prime, C prime, we call this as the tie line. Okay, so anywhere in this kind of envelope region, we are going to have, for example, here is a standard liquid vapor mixture, and then we need to figure out what would be the tie line. So that is the two corresponding liquid and vapor phase. Okay, so this is the diagram, and we should be able to calculate and construct the diagram by ourselves. And then, of course, there's two other special values. This is called the saturation. This is the saturation temperature. This is the saturation temperature of component 1. It's corresponding to okay. So that is a pure component 1 and 2 phase. Excuse me. So on the other side, if we try to use the pressure as the parameter, then we need to understand what would be the temperature for the discussion. So this is the curve pressure as a function of x and y. And still the first task would be to identify where is the liquid region. So here, if we are thinking about the high pressure, if we have a vapor phase and you keep increasing the pressure, eventually you are going to have a liquid phase. So with that justification, the up region would be now is the liquid region, and the lower part would be the vapor region. And then we are going to
Professor, it froze for like 10 seconds.
okay. Uh, yeah, I can see that the slides has not, no. Well, let me move to the living room.
All right.
Give me a minute.
I mean, if you want to take us a tour around the house, that is also cool.
Nothing special. So I'm a very poor faculty of chemical engineering, so I don't have a fancy house. It's just a place.
Are there any rich faculty?
Yes, yes. You can tell by the age.
Oh, you have more time to save money, huh?
That's right. Yeah, that's exactly the truth. So time, you can easily plot knowledge, and you know your. Thank you, Grace. I have to switch with my daughter. Say hello to my class.
Hello.
Hello.
She is having her Zoom studies, so I have to force her to my study. I'm using her table.
I like that picture setup. As we came out of that room, there's a bunch of pictures everywhere. I have not seen that. I like
Let me
it.
show you.
Oh, wow.
This is her Lego project, and she finished this last week. The bridge, the London
Oh,
Bridge.
is this the project she was working on when I came into tutoring?
Yeah, that's right. She was trying to show me the progress, and finally she finished that. And here we have the display for her Legos.
Wow.
That's the
Aw.
other one.
It's awesome.
Yeah. Well, we have to come back to business.
Nice break.
Thank you. All right. I have to switch my Wi-Fi, so I may be out of connection for a minute. Okay, are you able to see the slide?
Yeah.
Great. So I was talking about that when you have the PXY diagram, still the first task is to identify where would be the liquid, where would be the vapor, because we need to understand that so we don't make any mistake to identify this is my PX, the liquid line, this is the corresponding vapor line. And then the analysis would be very much similar to the TXY diagram. We have the saturation pressure for the pure component. We are going to have the analysis where you are going to move from the liquid phase, and you try to have the first bubble over here, right? So that is PB is still the bubble pressure. Or on the other side, if you are moving from the composition D all the way up to the mixture region, then PC would be the DO. This is the DO pressure, this is the bubble pressure calculation, right? So make a note that here we can easily see that when you are working on the vapor liquid mixture, you notice that the bubble pressure is always a little bit higher than the DO pressure, right? So this is the PB, this is the PC. You can see that the bubble pressure is always higher than the DO pressure. We will need that when we move on to the flash calculation in a few minutes. So this is the PXY diagram. And now I have to challenge you with the 3-dimension phase diagram. And I want to strongly recommend you spend some time reading the corresponding part of chapter 12. This is the very interesting part of the book as well. And I would appreciate if you spend some time reading those phase diagram. So now let's try to take a look at if we are putting the pressure and temperature and liquid vapor composition together, then we are going to have this quite interesting phase diagram, three-dimensional phase diagram. So as I have on the left-hand side for the nodes, so you can see that for the first node, try to check the facts. We have the species. So here is the pure species of 2, right? Because x1 goes 0. So that is a pure 2. Here is the place for pure 1 because x1 goes 1, right? And you can see that this this P over here, the pressure at the location of R, if you compare that with pressure of the location of condition U, then we can see that PR reading from the diagram is greater, is larger than the pressure at the condition of U. So this is why the species 1 is more volatile, or that species 1 is a light component. So lighter means if you increase the temperature simultaneously, then the component 1 can easily be phase transformed into the vapor phase. Okay. And then using the very similar analysis, we are able to tell that the up part, or here is the lower surface, is the vapor state. So that is the lower part would be the vapor. And then the upper part would be the liquid. Still using the same analysis that you start with the lower pressure, you keep increasing the pressure, you should be able to drive your vapor into the liquid. So this is how roughly you are going to identify which is the surface of vapor and what is the surface of the liquid. And of course, the upper surface would be liquid, lower face would be the vapor. And also over here, you can see that we are having the very interesting curve. So if you are following my iPad, the highlight. So when you read this line for UBHC2, UBHC2, we are looking at pure component 2 all the way up to high pressure, high temperature region. And C2 is the critical point of the pure component 2, right? Similarly, if you are trying to read this RKAC1, this is RKAC1, then this is a pure component 1 all the way up to the critical temperature at C1. And anywhere between the two lines, we are going to have the mixture. And the mixture will have their own corresponding critical condition. So this is why over there, you are going to have the curve to describe the critical condition of the mixture. Okay. So that is a very good diagram for the morning, right? So if we move on, I have a little bit more notes. Oops, I need my tea. The saturated vapor and the vapor and liquid will meet. They will meet along those lines. So let's say we are going to have RKAC1. So this is RKAC1. Well, this is what we just described, right? That would be the pure component, and we are going to describe one is for their pure species. So this is RKAC1. This is the UBHC2. So that would be the pure 1, pure 2, and they are going to meet to the up is the liquid, lower part is the vapor. They are going to also meet along the two borders of the pure species. And then the other note says a region bounded by these pure species, vapor pressure curve, and the critical lotus defines the phase envelope. So the whole shaded part over there would be the phase envelope, right? So there we have to have the liquid vapor mixtures. Anywhere over here, we are going to have liquid vapor mixtures. So that is why we sometimes we call this as a phase envelope. You may hear that name before. So this is the exact shape of the phase envelope. And then, of course, any point in the phase envelope will separate into vapor liquid phases. And that's indeed the reason why we will discuss the flash calculation in a few minutes. So there you say that is one point within the phase envelope, within the shaded three-dimensional area, and you just cannot keep the phase split over there. So automatically it will split into the liquid part at equilibrium with the corresponding vapor part. Okay. And then, of course, you can manipulate the temperature and pressure in order to have more liquid or more vapor. So on the next slide, the slide shown here is this is nothing special. If we keep moving out of the phase envelope more into the high pressure region, then we are going to have the subcooled liquid. If we move lower, again out of the phase envelope region, we are going to have the superheated. So this is the superheated vapor. Okay. Then we need to look at the way we are going to run those analysis, like we did for the two-dimensional diagram. So this is how we start with the liquid. So if we pay attention, here we are having this liquid condition F. So that is above the phase envelope. And then we try to lower the pressure. We try to lower the pressure. And then this line F will have the interaction, have the intercept with the phase envelope at this condition L. So for L, it's moving from the liquid phase. We are going to have the first bubble, right? So this is why we are going to have this as the bubble point. So the liquid L is a bubble point because we are welcoming the first bubble. And then, of course, if you are going to, so this is still the liquid line. This is the liquid line. And you are going to have the corresponding vapor line over here, liquid line. So this is the vapor line. Then when the system is at the condition L, then you are going to receive, this is a timeline, right? So over there, you are going to read the values for the equilibrium vapor composition. So this will tell you Y1, and of course, you're going to have the Y2 value. All right, so this is what we refer as the tie lines connecting the liquid and vapor at this fixed temperature and pressure.
Dr. Huang?
Yep.
I appreciate you going into detail in these graphs. It's helpful. I was wondering if we have to be able to use these graphs on the test on Tuesday.
I know you will have the question. The answer is sadly no.
Okay, that's disappointing.
But I hope you or the majority of the class would be still interested in reading the diagram. And my personal experience, I had one month internship with the BASF in China when I was a senior chemical engineering student. And for that 1 month, for that internship, we were simply reading all those phase diagrams. There's no exam, no test, no redesign, but the purpose to be the future chemical engineer for BASF for that production line is we need to understand what is going on just in case something happens. So this is why last night when I was going over my slides, I know that is not covered by the exam, but I still want to spend 20 minutes to go over those. So hopefully I can share some insight in reading those diagrams. So that's a great question, and that is why I said sadly it's not covered in the exam, but it will be very useful to some of you if you decide to stay in the chemical engineering industry. At some point, the phase diagrams would be very valuable reference for the production. Okay. And I know it's not too easy to visualize the diagram. And I was reading the textbook again last night, and it's not easy to read that a few pages. So this is why I decided to add some notes. So hopefully when you come back, revisit the lecture video together with those pages in the textbook, I hope everything will be much easier.
Appreciate it.
Great, thank you. So this is the same kind of analysis we take care of the upper region, right? The region above is the supercooled. Now you see what's coming. The region below would be superheated. Keep it in mind the pressure effect on the phase. I think as long as we have the daily life experience, increases the temperature, we are driving liquid to vapor. Increases the pressure, we are driving the vapor into liquid, then we should be able to identify the regions. And then the analysis is very similar. So now we are moving. So that point G is not on the phase envelope, it's actually above the phase envelope. So now we are moving, we are increasing the pressure, moving the vapor. So that is a vapor. We are moving the vapor up to have the first intersect with the phase envelope. So over there, we are going to have the first liquid job. So this is why we call this point G will be the dew point. Of course, we are going to have the first liquid job forming, and we are going to have the dew point surface over there. So that's curve. The curve when you are going to interact. Let me change my. So there you are going to have the curve of the dew surface. Okay, and then of course you are going to have the corresponding. So try to draw the tie line. So that would be your corresponding liquid at equilibrium to the condition W. So over here, you're going to have this is a tie line, and there you're going to read the corresponding X1 value.
Why is the tie line diagonal?
Well, it's the visualization curved by my terrible drawing.
Okay.
So it should be horizontal with respect to the surface. Okay. And you would kill me by this diagram, right? But I still have to say something about the diagram. So that is how we are going to try to convert from 3-dimensional to the 2-dimensional phase diagram. So remember we have this P, T, X, and Y diagram. So there we try to, for the actual production, we may fix the temperature, and we try to understand what would be the pressure effect. So this is why we need to start from the 3-dimensional diagram in order to receive the 2-dimensional. Okay. And then we also need to have this temperature TXY diagram. So we're pretty happy about the TA. So if we look at this temperature at A, we should be able to identify this is a liquid line. That is the vapor line. And similarly, if we are going to look at the temperature XY diagram, then we are going to have this lower part as my liquid line, and that would be my vapor line. This is number one. Number two is you notice that something is interesting when you are changing the temperature, right? And I want to ask you, what is TA is smaller than TB or TA is greater than TB?
I'll vote the latter.
That is the answer, right? And it should be quite easy to see because we don't have any critical temperature over here. We don't have any critical condition over there. But if we moving from TA to TB to TD to TC, then we are going to have the critical. So we are getting closer to the critical region. So that's how you try to convince yourself that the temperature is increasing.
So even though you're increasing the temperature, you're going from vapor to liquid because pressure is increasing?
The pressure is always changing over there. So here the key point is we try to identify which temperature is the highest one of the three.
Okay. And that it's because the critical point is up.
Yes. So when you move up, at some point you are going to have the critical condition shown on the diagram. Then this is the high temperature region. Very similarly, you are going to have the pressure increasing. So those would be my kind of personal tips when you try to identify what is the order, what is the corresponding region. Try to somehow justify using daily life experience. For the vapor, it would be stable at high temperature but low pressure, right? So you use those known facts to convince you where would be the proper region for those. So now the question is, how do we receive those interesting, let alone why you are going to have the two intercepts with the borderline, but why we cannot have the intercept on the right hand side. So now if you go back to the two-dimensional, let's try to find a clean one to start with. Yeah, maybe that's a good one. So you can see that if we are more interested in the PXY diagram, then we need to somehow fix the temperature, right? So that is the temperature X. So in order to have the fixed temperature curve, then we need to have this, I know this is challenging, this is the vertical cut. So when you look at the plane moving from E, so that's the temperature of TE, that's a fixed temperature. If we are looking at the plane perpendicular to the temperature curve, so if we are looking at this plane E, A, that's the A, F, no, L, that's the L, go into B, go into D, coming back to E, that will be my plane. So this is the, EA, when you have this cut, then you have this fixed temperature, right? Then you are going to have the PXY. Okay. So this is how you are going to receive. Now when you try to look at the when you try to look at the so that blue shaded region would be the first one we see. So that would be this one, right? And then of course, if you are moving along the temperature, say if you are going to cut over there, then you will have this kind of shape. Okay. So this is what we are going to have the pxy. Let's try to take a look at the txy. Now this looks like a very ugly diagram. So in order to have the fixed pressure cut, then we need to start from, say, let me try to get another color. We need to start from this PU. Okay. So now instead of having this vertical, we need to have this horizontal cut. So over there, if you are looking at this K, J, L, I, H. Then L back to K. So this is following K to J to I to H to L all the way back to K. So that is how you are going to define at this fixed pressure of U. Then you are going to have this horizontal curve, and this is how you are going to receive the shaded area. Let me try to. Looks like my iPad does not cooperate. I thought iPad is much smarter than me, but looks like not. I see. So that white region would be the one we are going to see on this line. Okay, I don't want to further torture you guys, but that's a quick note. If you happen to read the phase diagram and you wonder how do I receive this figure 12.2, then I hope that I have shared some thoughts with you. Okay. Then the last diagram, well, we have the slides. The last diagram is for the PT diagram, right? So we have this PT XY, then we could have PXY, we could have txy, and eventually we could have the pt. So this is how we go from the 3-dimensional to the 2-dimensional phase diagram. So when you look at that diagram, then I'm not planning to do what it. Let's try to test. Well, this is the diagram when you are going to have m. So now when you try to have the fixed value and you are going to have this cut. And I don't know how to describe the direction, but let's try to write down the critical points. So let's move from M to L, L to S, S moving back to W, and W move to N, and we try to have this curve. So that's a shape we are going to have. And over that region, so that is a region. That would be my fixed composition part. So this is how we are going to receive this PT diagram. And then over here, you are going to have the first as a pure one. The last part would be pure two, connected by, we call this as a critical lotus line. And any line in between, you are going to have the liquid. So this is the liquid, this is the vapor. I know you guys are completely lost. So I'll just stop here, right? So I give
I'm
you
on track. You can keep going.
no feedback, so that does not excite me. So I give you this fig a minute. Let me try to get some water. Okay, I'll be back in a minute.
The graph kind of looks like a jellyfish.
How do you see a jellyfish?
How do you not see a jellyfish? Let me.
This arch up here is on the critical locus is the box, and then all these lines are
The tendrils.
Y'all are dumb.
What? No, it looks like a jellyfish. Everyone, it's just you on here. Doesn't see the jellyfish.
So you see that it's not fair. As long as I stop or as long as I disappear, you guys are very happy talking to each other, having some fun chats. But when I'm here, then this is boring.
Dr. Hong, correlation is not causation. Is that
Yeah, we're just serious, Professor.
We were examining the graph.
Yeah, I mean, you want to join us in? You've got headphones. You surely heard. Does it look like a jellyfish to you or not? Anahita apparently cannot see it, and she is the only one in the class.
Layla doesn't see it either, so.
Well, I respect your imagination, but this is a phase diagram.
Oh.
All right, let's move on to the next part. So again, the phase diagram is kind of very interesting, and I think that is also a good opportunity. I think every chemical engineering faculty is kind of struggling to show the 3-dimensional phase diagram. So I wonder why nobody is trying to use some computer science, trying to have the video to clearly show, when you click, you see the 3-dimensional, and then slowly having the motion to clearly illustrate. So I may hire some people to do research with me and try to somehow generate the 3-dimensional phase diagram video model. But anyway, that's a side note. Let's move to the flash calculation. So this is a very typical industry. I have a container where we are going to have the liquid and vapor. Looks like we are going to control the temperature and pressure. Looks like we are going to have the phase separating over there. Looks like we have to have the feed. So the general problem setup is I have the temperature and pressure, and I can manipulate that. Let me change the color. iPad is a bit strange. Now I lose the iPad again. Okay, so I could easily tune temperature and pressure. Nevertheless, the total volume normally is fixed by the existing of the container. I can change the feed. So this is the feed. By feed, we are going to have a choice. And in practice, it would be much easier if we start with the liquid. Why? Because liquid is much easier to transport and much safer, right? So this is why if you go to industry, the majority of the feed would be the liquid. However, in order to make it very general, let's try to acknowledge that we may have the feed as the mixture of the vapor and liquid. And of course, over there for the vapor, using the binary system as an example, you're going to have X1 and X2. Oh, no, that's vapor. So this is Y1, Y2. For the liquid, you are going to have X1 and X2. So what? Now the question is, well, we have this feed at maybe T naught, maybe P naught, and we are ready to use that feed for some production. And we need to tune, we are going to change the feed thermal condition to a different temperature and pressure. And we need to understand, well, what would be the fate to that feed? Are we going to have phase splitting? Are we going to have the liquid transformed into vapor or the opposite? So this is why we have the name of flash. Simply we try to understand the phase from liquid to vapor or vapor to liquid. And if we have the change, then for the equilibrium, what would be the composition? What would be the X1, Y1, right? So that might be the final X1 prime and Y1 prime. So that is the very general problem statement that we have. And you may think of some other cases, say, I do have a mixture, liquid and vapor. However, when we are going to, I try to have a simplified code. I start with a pure liquid. If I have the pure liquid, which is X1 and X2 at T naught, P naught. So now using this flash calculation, changing the temperature and pressure, I may still have the liquid. That is because we need to satisfy, if you recall, we need to satisfy this bubble pressure in order to make the first bubble, right? So if at that condition, the bubble pressure is greater than the specified pressure, then you cannot have any bubble because you have not reached this critical pressure to form the first bubble. The same story, if you have this pure vapor, then for some rare cases, you may remain as the pure vapor mixture, let's call this mixture, because we are going to have Y1 and Y2. You may have the rare event that is after this treatment, you still have this as the pure vapor. That is because you have not satisfied the dual pressure requirement. Okay, so that would be these two special cases. And that is why the previous discussion, the 4 types VLE calculations are relevant in order to move on and understand the fresh calculation. So that is the first note, and I hope you still recall what would be the, if we move on all the way, so that would be, if this is the pressure, if this is X and Y, the high pressure, this is the liquid region. Low pressure, this is the vapor region. Vapor moving to the liquid region, this is the dew pressure, right? On the other side, if we are moving from the liquid to have the first vapor, first bubble, we call this as the bubble. So clearly you can see that we need to satisfy the requirement, the eventually temperature should be in between this region in order to maintain the equilibrium liquid vapor mixture. Is that clear? That's quite important. So let's try to make sure we are good on this.
I'm sorry, can you restate that?
Restate is if I have this as the can you be a little bit more convenient, iPad? So if we start with A is my initial, right? A is my feed. This is A. Then if I change the temperature, or here is changing the pressure, so apparently you can see this is P naught for the initial feed at P naught. If I control, if the tower is at P1, say this is P1. Then you can see that that's not very useful. We have the feed into the tower, but the pressure inside the tower is not high enough. So there we are going to still have the still pure vapor mixture. So the only change is now we are changing the system into this point B over here. Simply because the pressure is still lower than the dew pressure. All right.
Yeah, gotcha. Thank you. I was just writing some stuff down earlier.
Then if on the other side, if the pressure is at P2, P2 is over here. Okay. This is P2. Then you can see that the P2 is even greater than the bubble pressure. Then you can see that we are going to convert all the vapor into the liquid, 100% liquid mixture. All right. So here we are going to have the pure liquid mixture. For many chemical productions, we want to maintain liquid and vapor for the kinetic purpose, for the transport purposes. So this is why we need to maintain the P over there. So the pressure over there should be from the dew should be greater than the corresponding dew pressure, should be smaller than the bubble pressure. If that is the case, then we are going to maintain liquid and vapor mixture. Is that clear?
Yeah, that's clear.
Okay, great. So let's move on to have the very general symbols and a few analysis, a few equations, and eventually let's have one example to understand the whole process of calculation. First of all, we always start with this 1 mole. So for the feed, we try to use 1 mole. So that is a per mole based analysis. And we try to look at this overall feed composition. So for I component, we try to use a feed. So this feed is 1 mole. Then for any component, for any I, we have this Zi. Zi is the overall molar fraction of a component I. So we need to have the molar fraction out of the liquid phase, out of the vapor phase, in order to understand the Zi. So that is defined by the two equations over here. So now if we have the feed and we know that we try to have the flash, we are going to have the phase splitting. So now we are going to have the liquid and the vapor. So that is the liquid mixture. And of course, that is a vapor mixture. So that the sum of the two would be 1 mole, right? And then if we are going to have the Xi, the liquid molar fraction for component I, Yi, vapor molar fraction for I, then if we know the number of moles for the liquid and vapor, then we can calculate what would be the Zi value for each component. All right. Moving next, we know that L and V, they can be reduced. So there we try to reduce, get rid of this liquid. Okay, we try to understand how we are going to calculate the Xi, Yi, or Zi here using the understanding of the vapor. So now liquid is simply 1 minus V. So this is 1 mole. This is V mole. Then we are going to receive this new equation over there. So what's the use of that equation? Well, we are going to have the Zi value, but on the right-hand side, we are going to have the Xi and the Yi. So you may not see what's the use of this, but I hope you are convinced that if we are using this capital K, then we are able to get rid of this Xi or Yi by the Ki values, right? So there we are sticking with the vapor, right? Vapor shall always talk with the Yi values. So this is why let's try to get rid of this Xi, okay? By Xi would it be Yi over Ki. So now if you plug in this value, Xi is the function of Yi, you see the Yi over Ki, then we are able to receive this equation. And you may still feel a little bit confused why we are doing this. Well, be patient, we shall see the reason in a few minutes. So now when you have this Yi value, and we understand that summation of all those Y components shall be 1. Similarly, if you try to add up all those Xi values, this will be always 1. So this is why now we are able to express all the components in the vapor phase by the corresponding number of mole of the vapor, those Ki value, and hopefully the Zi value. Zi is from the feed, right? Zi is from the feed. Then we can run this equation 13106. which is we just add up all those yi value. So now you have this summation form for all the components. You shall eventually receive this equation. So now let's try to look at what's going on. What's the use of that? Well, we know the zi. Zi is from the feed, right? But we don't know the ki. How about the ki? We don't know the ki. And the whole purpose of this equation is we try to figure out the v after the treatment, after manipulating temperature and pressure by the flash process. We need to understand the vapor phase number of moles and liquid phase number of moles, right? So that is the purpose of the flash calculation. Looks like we are limited by the ki. What is that ki? What is ki? Well, if we cannot quickly have the answer, let's try to go back to the definition. Definition is always the key. Ki is yi and xi. Still completely have no idea. What's the use of yi and the xi as a ratio?
Can you relate it to pressure?
Getting closer, yes, keep thinking. You know the pressure. Yi is the vapor phase, xi is the liquid phase. At
Rounds,
equilibrium, what?
Round law?
Even closer.
Even closer.
So the answer is indeed, it's coming out of the two phases at equilibrium, right? So we have this, I know you don't like it, fugacity. If we simplify this, or if we try to look at this very general equation,
Your t-shirt equation.
yeah, my t-shirt, you still owe me that t-shirt, the class owe me that t-shirt. Right? Now if you think about that, what is yi? Yi over xi. Right? So that's the equation. So you see that we're always in the loop of calculating fugacity coefficient, calculating activity coefficient. Right? And that is the most general case. So somehow if we are able to simplify, this is kind of the low pressure, we are trying to deal with the very similar petroleum engineering molecules, C5, C6, then we will be very happy to realize, hey boy, this is just one, because we can treat this as the ideal solution. And the pressure is not terribly high, so we can use the ideal gas equation. So at some point, for many problems, yi over xi is simply pi set over the total pressure. This is the pressure we are going to control. Pi set, if we know the temperature from the Antonio equation, we have the pi set, right? So that is the answer. That is the answer. For the ki, right? So now we know the feed, we know the ki, and we are able to solve after the process what would be the moles of vapor and liquid, and everything should be straightforward to calculate. Okay. So that's a core part of flash calculation. All right.
Okay.
So I'm going to skip the next line. you may feel a little bit confused. I have the slide simply because I want to show you on this slide and next slide, there are some thoughts about the actual mathematical methods. So this is why I decided to also include this slide. You can read the textbook and try to figure it out over there. So why we have this, why we define this fy function, why we define this fx function, why we try to combine the two, trying to have the f function. And I want to point you to the Newton's method, and the textbook has the appendix to show you what is going on for the method, okay? So the remaining is simply the algorithm part for many softwares that are designed for the flash calculations. What's behind those keyboard input. So that is the Newton's method for calculating the roots of this equation. And normally that will be a cubic equation for the vapor volume over there. So we have a few minutes. I want to go over the example. But before that, I want to quickly show you that two equation. Okay, so are we happy with this equation? This is one of the three equations, right? This is the vapor phase, sort of the ideal gas treatment. So I know this is a low pressure. On the liquid side, I have to calculate the activity coefficient. So this is a non-ideal low pressure for the vapor phase, non-ideal for the liquid solution, right? So that is the case. So the use of this equation is I want to quickly show you how we are going to calculate the total pressure from the liquid phase or vapor phase. That is because we need to figure out the dual pressure and the bubble pressure. The reason is we need to figure it out to tell whether if the flash calculation is available. Like we just discussed, if I did a bad calculation, so you are the production line engineer and you did a bad calculation because of thermal, and you had a bad control of the pressure of your production line, and you put the pressure control over there, then there's no flash calculation. There's no phase split. Okay, and if you are if you did a bad calculation again, you use a too high temperature over there, then there's a pure other phase, not liquid vapor mixture. So we have to make sure that this is a region for my pressure control. So that's a sweet spot for my manipulation. And keep this slide for your future calculation. So there we need to figure out how I'm going to calculate if I'm moving from the vapor phase. If I'm moving from the vapor phase, then I need to figure out that if I'm moving from vapor, then this is about the first dual, right? So this is the dual pressure. If I'm moving from liquid, I'm going to calculate the bubble pressure. And then starting from this phase equilibrium equation, we are going to have the manipulation. One is I try to have, if we are looking at this equation, then I'm trying to express this yi as xi pi set over p total. And I know that for the vapor phase, I'm going to have the summation of y would be 1. So this is the way you apply the summation to the that would be the one. So this is how you try to put the total pressure out of the summation term. Okay. On the other side, if we are moving from the liquid phase, we try to figure out the bubble pressure. Then this is the xi would it be all right. So then we again apply the summation form. This is 1, meaning I'm going to have yi p over activity coefficient pi set. This would be 1. So there, the pressure is a constant. So I put the pressure outside of the summation term. Then I'm going to have this equation. Okay. So that is the two very important equations for the door pressure and the bubble pressure calculation, knowing yi value or knowing xi value. Okay. So now let's move on. I want to spend the last 2 minutes on this problem. So it says the system, we are going to have 3 components, 1, 2, and 3. We know the temperature, we know the pressure, and by the way, this is the textbook example. We know the temperature and we know the pressure. So and we know this the overall composition, right? Assuming Roche law is appropriate to the system, meaning we are able to use yi p xi pi set. We need to determine the liquid phase, vapor phase, and xi and yi values. The other known information is at this temperature, we know the 3 saturation pressure. Right. So I will not go into details, but when you read the textbook, you may feel a little bit lost. What's going on? How do we calculate the bubble pressure and door pressure? First of all, we need to determine whether this known KPA is indeed between door and bubble. Okay, so that's the first step. We need to always evaluate for the known condition, what's the door pressure and what's the bubble. Secondly, you can see that from the previous slide, we need to have those xi or yi in order to calculate the corresponding bubble pressure and door pressure. But from the problem statement, we only have the zi value. So that's the other thing I want to quickly share with you. So you see that the zi is what? From the definition. From the definition is xi v plus yi. No, sorry. Is xi liquid yi of v. All right. So now when you are moving from liquid. So if this is a pure liquid, you are going to look for the first bubble. So this is the bubble. Okay. Also at that condition, when you have the liquid, then this L would be 1. because that's a liquid. I don't have any vapor yet. So then this Zi is your corresponding Xi. Okay. On the other side, when you try to figure out the dew pressure, which means you are starting from the pure vapor and you are looking for this dew pressure. Then for the pure vapor, you are going to have V as 1, liquid as 0, because there's no liquid at all. So now when you try to come back to this Zi, then Zi is now is converted to Yi. Right? I want to add that two equations so that when you come back to read the example, I hope it would be much easier. Okay, I'll share the lecture note. And lastly, we are having 36, and I want everybody to leave a hello to the chat. I'm going to collect that in the end. I noticed that for the past at least 4 lectures, we always have around 60 some students. So I want to collect that so that I'll think of some ways to have a bonus. So try to leave a hello, just hello to the chat. All right.
How much of a bonus? How much of a bonus we talking?
Have no idea. Maybe 30 points. All right.
I'll fix my previous grade from this test.
I'm glad. I'm
No.
glad I show up to class.
All right. Thank you, guys. We'll come back to the weekend and come with the questions. Right.
Sweet. Have a good day.
I have one question. When it's not ideal